Here we are, yes, recording. Here we're going to have a look at moment of inertia. Okay. Now, what we did yesterday was we had him, we spun him around with his legs straight, and we just saw how many times he rotated. Then we actually had his legs in, we spun him around to see how long he'd rotate. And it worked nice for you guys because you had the first one you rotated 5, and the second one when it was a smaller moment of inertia it was 8, I think. Yeah. But the other group didn't. It worked the opposite. So it was on the chair. All I want to do is just one experiment today, and that is what we're going to do is he's going to keep his legs out to start with. Okay, so at the moment, the moment of inertia, is it starts from the axis, which is the base of that, all right, all the way down to the end of the mass. Okay, so the mass is distributed quite far away from that axis. So that means that the moment of inertia is quite large. We all understand that. So it's going to take more force for me to move this now, as it would, so bend your legs, if I was to now try and move this. Does that make sense? So that's easier for me to move than it would be this. Okay? Because the mass is distributed closer to the center or the axis of rotation. Okay? So the moment of inertia is smaller. And what is inertia?
An opposite or equal resistance of a body.
The resistance of a body to any movement, or a change in movement. So, so something will stay in a sort of a uniform movement, or still until acted upon by an unbalanced and external force. Understand? All good? So here, the moment of inertia is smaller, so therefore the inertia is smaller, it's easier to move. When it's a large moment of inertia, then actually it's harder to move. Now, all I'm going to do today is we're going to have a quick look at the angular velocity. Okay? How does the moment of inertia change the angular velocity? That's what we're going to have a look at now. Alright? That's what we're going to have a look at. Okay? So you're ready? So you're going to keep your legs out until I say bring them in. Okay? Okay, bring them in.
Cool.
Okay. Good. Stop. We'll do it one more time. Okay. Bring them in. Stop. So, what is the correlation between moment of inertia and angular velocity?
The greater the moment of inertia, the greater the amount of force is needed to have the same angular velocity.
Forget about force, take force out of it for the simplification reasons. What's the correlation between moment of inertia and angular velocity? Lower. Yeah, slower the angular velocity.
Does that not mean with the same force?
That complicates it because if it's a large moment of inertia, it's going to be harder to move. Yeah? So I just want to keep it really simple. Okay? So just think about that correlation between the two. Because in the exam, you're not going to be asked about the force. You're only going to be asked to draw a diagram to represent, what happens to angular velocity, what happens to the moment of inertia in that movement, and what happens to momentum. Okay? So let's keep it simple for that for now. We might have time to go on to discussions about the force. Now, here you saw in that motion the moment of inertia when it was long. Yes, he was spinning around, so the angular velocity was a certain amount of radians per second. Okay, but as soon as he brought his knees in, it almost it was significant change, wasn't it? Massive change. All right, and all of a sudden, the angular velocity increased, and he spun around a lot quicker. So therefore, we know that there's a correlation there. There's a significant correlation between the two. Happy with that? On the board here, you've got. Thanks, Joe. You can go sit down again now. On the board here, we have sort of a bit of a really simple diagram. Okay, really simple diagram to show you. Okay, rotational inertia equals mass times square distance from the axis. Okay, we know that. Distance of mass from the axis squared. Okay? Alright? So that arm was longer, then the moment of inertia would be larger. Okay? And therefore, what would happen, okay, let's say, for example, we use the same force, what would happen to the angular velocity? If that moment arm got longer, the angular velocity would slow down. Okay? Right. Excellent. So for now, that's all I sort of need you to sort of think about. Okay? Now, here's some interesting examples. Yes?
Just to clarify, so is angular velocity the velocity of something going in a circle?
Yes, it's a rotational velocity. So and we're looking at angular motion at the moment. So everything is in a degrees per radians per second. This is a really good example of how we've all evolved. Okay, I don't know if you can see that, but basically you've got a cheetah, the fastest land animal. Okay, on the right here, the bulk of its mass is in the glute. Okay, close to the axis of rotation. So when this animal, okay, wants to move that leg really quickly, it means that most of the mass is closer towards the axis of rotation. So that means that the moment of inertia of that animal's leg is really small. So that means the angular velocity, so the speed at which they can bring that leg down, is going to be so much more. Okay, so that's why your top sprinters, okay, have got the bulk of their musculature in the glutes and maybe the quads. Okay, there's not many sprinters which have got really big, heavy legs, because the moment that would increase the moment of inertia, they'd be able to move, the hip extension would take longer and they wouldn't be as fast. Okay, same thing again, we've got very fast, like little deers, so you can see it very obviously there. Bulk of the musculature is in the glute and the quad, and then you see the lower part of the limb is pretty much just bone and tendons, yeah, because that just allows for that smaller moment arm, really fast movement. Okay, and then the human being itself as well, so generally our quads are bigger than the lower limb for that particular reason as well. Okay, right. Now, can you do me a favour? On your graph that you drew, can you draw in the position, the right positions, 3 diagrams of somebody doing the somersault? So that table that you drew, like this, you need to draw. What would the position be here? So here, they're rotating at 6 radians per second. Yeah? So angular velocity here is 6 radians per second. So what kind of position would they be in? Would they be in a tucked or more of an open position? And then here, they're going at 24 radians per second. Therefore, what kind of body position would they be in? Okay, so just a quick little diagram underneath that diagram that you did. All right, guys. Thank you.
Should I copy out that other diagram?
Do a sketch for that.
Yeah, I'm
Just draw the things first, and then
Can
I draw the activities on the top of the page? Just this one here. Okay. Yeah, you need to practice doing that. So if you're looking at that data from the table, you can plot a graph. Okay, that's a skill in itself. Yeah. So you can put it on the actual diagram if you want, or underneath it. That's fine. Just do that.
You just said, I stole these off you.
No, you said they like what?
Just keep it simple. Don't worry about like work of art or anything like that. I just need to know that you can have a look at the graph and you can say why has the angular velocity increased? What's changed about the body shape?
So, I don't know if you remember, but I did the graph quite badly, so I ripped the page out. But shall I just do a quick sketch just to like?
We'll do what I said for Kitty to do.
Yeah.
So just draw 3, 1, 2, 3
Yeah.
body shapes, and then above that you can do the diagram.
Okay.
Okay.
Yeah.
Let's not take too long about this. We're going to move on. Just a stick figure is pretty much all you have to draw. there's my stick figures right there. Okay. So as you can see here, the body is more extended. More extended. Center of mass is distributed quite far away from the mass is distributed quite far away from the center of mass. And then here, the center of mass is in the middle of the body, and the mass is distributed closer towards that. And then afterwards, okay, the body extends out again, and the mass is then distributed further away from the center of mass. That means that angular velocity is low here, angular velocity is high here, and then angular velocity slows down again because of that. Cool. Okay, on your worksheet then, just fill in those definitions please, if you haven't already done so. So, we're looking at moment of inertia, okay? Yes, sorry. It's that moment of inertia, right? Some people have done it already, which is great.
Yeah, I just haven't put the equation in there. Actually,
Jack, quick challenge for you, dude, who's looking a bit bored. Tell me, without looking at the book, how do you calculate the moment of inertia?
It was measured in kilogram meters. Kilogram meters squared. So it would have to be mass. Something about mass.
Think about, look at me, don't look down. Joe's legs.
Yeah.
Okay? His moment of inertia was high when his legs
Oh,
were
it was
extended.
distance from mass times distance from axis of squares.
Am I correct? Kilogram meter squared, it is, right?
Yeah, that's why I'm trying to figure out how you got
You think that one's difficult, right? Wait until like
So the
momentum.
next one is kilogram meters
that's really
squared
good. That.
per radian times radian per second. So it's
Kilograms meters
That's
squared.
crazy. That's, yeah, I know.
Terrific. Well, he does
Probably-
maths A levels, so probably isn't that crazy.
What's that, sorry?
Jack does maths A levels, probably not crazy.
Ah,
Maths, he did flip maths.
got that mathematical mind. Right, happy with that, everybody? Yeah? So you all understand, you'd be able to define what moment of inertia is, okay? You can hopefully, if you understand the calculation for it, then you should understand the definition for it. Does that make sense? Because that's the way you did it. You worked back from the units
Yeah.
to the calculation, and then if you were asked to describe it in words, you'd be able to do that. Right?
Yeah.
Cool. Next one. So,
Wait, what? Is that meant to be a square?
Yeah.
Distance from axis to, is that moment on?
right, now we're going to try and apply it. We're going to try and apply this now to three different situations. One, we've got a sprinter and their legs. Okay? A sprinter, I want you to tell me, how did they manipulate moment of inertia to improve performance? front crawl. Somebody performing a front crawl in swimming. How did they manipulate their arms to the moment of inertia of their arms to improve their performance? And then a high board diver performing somersault. Okay? So let's do that on little mini whiteboards to start with. So on your mini whiteboards, okay?
The resistance of a body to change its state. Or rotation. State of angular motion. With diagrams, how would you use them?
Are you guys all on this task now, or because I need to move on in like 5 minutes? Yeah? Right, just need to understand that we're on a bit of a time schedule here.
Just like a low right.
But what, think about, okay, what particular moment with the sprinter of the stride pattern does the moment of inertia change, right? Think about it yourselves. I don't want you to all share ideas. Try and think about it yourself. Okay? You've got preparation, execution, follow through of each stride. Yeah?
You want a specific time.
Yeah. You need to
None of those. None of those.
and then use, I said using a diagram. So on mini whiteboard, explain with diagrams, okay, how we can change the movement inertia. At what point does that have to walk right back? In the book, you pretty much write like half a page on the description of how it's done. But it has to be a bit more specific than that. Because at what? So while they're running, if you think about one leg, not both legs, just think of one leg. At some point, it's 40% really when what movement's going on? And then so what bends to help flexion of that? Well, if you think about it, you should be able to figure it out. Deeper thinking, that's all I'm asking.
Surely that's just the preparation.
You know what I mean? Like when the leg comes down, up and round.
Oh, I know, because they go long.
Yeah, exactly.
So you sort of like
Yeah, but they don't pull.
sort of reloading it to go back.
They're pulling.
You know what I mean?
It's pushed off the floor, fully
Yeah.
extended.
Yeah.
That happens.
Yeah. Because I don't think it's really
So-
follow through, is it?
No. The follow through is probably there, it's sort of pushing off there.
So it's the reload.
So it is recoil or recoil. But you therefore have to say what is the body doing to reduce the moment of inertia? And therefore, what movement is it allowing to happen quicker? So the two joints you're looking at. Paralympic athlete.
No, what are you laughing at?
Oh wow.
I
Trace
trace it, yes.
Are you
Yeah, but I think mine is traced best.
competition?
But the idea to trace it stems
So the brains and then the skill.
No, it's way more fun than drawing.
Wait, let's see it, Kitty.
Oh, Kitty, show me.
Oh, should we just talk about the first one?
Kitty, that's so smart.
Shall we just talk about the first one?
Kitty, that's all.
No responses? No?
Yes.
Yes, thank you, Jacob.
Jacob.
Good on you, Jacob.
Thank you.
Right, everybody, eyes this way. If you were to describe in an exam, if it says this could be a 10 marker, or could even be part of a 20 marker, where it's going to want you to apply all of these things to a sporting example. So you wouldn't get away with just saying, for a sprinter, they bend their leg and that reduces inertia. Done. Okay, so what you need to do is, okay, you've got sprinter, let's say that's the upper body. That's the upper body. Do with a black pen. So where did I put my?
Yeah,
No, I've got it here. Thank you. Right. First base. Okay. What they've done is we'll just focus on the one leg. Okay. So let's say we've got to the point where actually the knee down there. Okay, and toe off. Okay. The toe off's happened there. Everybody happy at that point there. Now what we need to do, what does that leg now need to do? So this other leg, okay, is coming through there, right? What do we need to do, so take this leg away again. What does this leg now need to do, Ben? Joe?
The knee drives up parallel to that sort of
No?
the foot. If you're saying the foot is the end of the moment arm, it needs to swing round, like so clockwise.
Just give me technical terminology. What joint are we talking about? The knee joint. What happens at the knee joint? Flexion. Simple. The knee, there's flexion at the knee. What is the result of flexion at the knee now? If it now starts to actually flex at the knee.
Angular velocity of the foot increases. That moves clockwise.
However, it's not necessarily angular velocity at that joint. It's the angular velocity at that joint. Okay?
Because that's now where the power's going to come from, is it?
Drive the leg forward.
There's no
Where's my red?
Snaps it back.
The knee goes up before the foot goes
So basically, that's the moment arm at the point at which there's toe off. Yeah? So we've got to there, bang, we pushed, yeah, to get the speed. Yeah? Now, this is now the moment arm when we flex at the knee. So all of a sudden, the moment of inertia has reduced. Which means now that I can actually recoil that leg, I can now then do what? What's the next motion of that? Coming through. Okay. And actually bring it from there. We want to bring it there and then to be able to snap it down again. And sprinters want to get their knees up really high. But if you look at somebody like Usain Bolt, right? He actually has an extreme amount of knee flexion during that recoil phase. And a lot of sprinters don't. Like the top sprinters have more of a knee flexion than the not so fast sprinters. Because if your knee flexion only happens to there when you're sprinting, what's the problem with that? What's greater? The moment arm and the moment of inertia. So therefore I can't move my limb as quickly to get it up high to then pull it down again. Does that make sense? So that's how you would describe there, using technical jargon, technical language, biomechanically speaking, how an athlete, a sprinter in particular, would manipulate the moment of inertia to improve performance. Are we all clear on that? Awesome. Right, look at the next one. Front crawl arms. Front crawl arms. So, let's think about the front crawl. Let's do this together. Because you guys look a bit sort of tired. Okay? Again, similar. It's cyclical, isn't it? Sprinting is cyclical. Yeah? Remember, my legs are sort of kind of just on a cycle of that. Now, front crawl, cyclical. It's on a cycle, yeah? So therefore, right, when does the limb extend?
as it comes over the ear.
Okay, good. As it comes over the ear, good. Before, okay, so once it leaves the water, I don't know why I did that. Okay? Once it leaves the water, right? What do we have to do with that arm? So we've pulled S shape. Don't know if any of you swimmers here. It's an S shape. We've got to there. The arms now.
I always thought you just.
Nah, for fluid dynamic reasons, and you'll be looking at that next time. Once you get to there, what then happens to that? What does that arm now have to do?
Flexion.
Flexion and what was it?
So this is what they say when they teach swimming: is this elbow has to lead. Why? What's happening? It shortens the moment arm. And you know what they do? They say as that arm's coming over, you basically drag your fingertips over the water, because it pretty much keeps the moment arm as short as possible. Rather than coming out the water, and a lot of people go all the way over, right? If I go all the way over like that to then cut into the water again, is that going to be faster or slower?
Slower.
It's going to be a lot slower because the moment arm's longer and the moment of inertia is greater, and therefore something is angular velocity is lower. Excellent. Use that technical language when you're describing these things. Okay, so swimming. Do you all understand that now? So basically, it's the recoil. What do they call it? The recoil or the preparation phase or recoil of the arm. So bringing that arm back over. Okay. There's flexion at the elbow to increase the angular velocity. Last one. High board diver. You should all know. High board diver. So I'm on a high board. Okay. Let's say I'm going backwards. From here, I'm going. What is creating the angular motion now?
It'd be after that phase.
Yeah. What's going to create the angle? So, what am I rotating around as a diver in air?
Where's your head? It's on the top of your head. Just straight.
No. Okay. When we spoke about the definition of angular motion, what did we say? Centre of mass. Good. So we're basically creating a what force around eccentric force created by the arms and the extension of the legs around that centre of mass. And now if I'm doing a backflip, the centre of mass is going to start actually sort of moving from my navel to behind my body. Okay? Now, if they want to do the back flip and then go into into rotating, and they need to perform 4 rotations before they hit the water, what do they have to do?
They pull their knees out here like that.
Yeah, excellent. Basically, you see,
It's like
they don't just go there, do they?
It's like a flat top.
Yeah, they don't even just go there. You see the top guys like Tom Daley, their legs are like almost by the ears, aren't they? So it's amazing, because they haven't just gone there, because that's actually, it's proven that that moment arm's probably bigger, so therefore the inertia is still greater than when they actually tuck them in, and they're so flexible, you get their knees almost here. So that means that every inch counts. So that moment of inertia's got even smaller, which means that the angular velocity increases even more, so that actually they can do the 4 rotations before gravity gets them into the water. Yeah? Cool. Excellent. Right. Now, you have to write down now the explanation that I've just gone through for just the 2. So, let's go with the sprinter. And you're doing this in your books. And the somersault. Okay? Yeah, write down the explanation of those 2. And, guys, an example, if you're struggling with it, in the book is, look how long this one is. There's all of that. All of that there explains just that rotation there. And that's a triple action. Okay, so it's probably going to be about a paragraph for each. And it's so bad. Okay, so now I've given you an individual task to do. Unfortunately, first, this is not your strength. Okay, as far. You need to just get on with the task, please, rather than just have a big social now. As soon as I've said, go and do something.
Maybe actually.
Let's get on with it, please. We're on a schedule. We've got things to get through. Okay, one paragraph describe each of those. In fact, you know what? Just for speed, just one. Do it well. Either the sprinter or the somersaulter.
Not front crawl.
No, no. So, I'm going to say the key words you have to include. There we go. Keywords to include in your explanation. You shouldn't really have to look in a book for this.
Kizzy's asking about eccentric, wasn't it? She wasn't there. That's what
Eccentric force. Okay, it's if you've got so if this is the person diving off the board, the backflip, yeah, they're going to go perform backflip. The eccentric force is pretty much acting. So the center of mass is here, right? The eccentric force is acting around the center of mass, not through the center of
Is
mass.
it like the force that makes them spin?
Yes, it will create an eccentric force is seen as a torque force as well, and that creates a rotation. But it can't be applied through the center of mass.
It's around.
Around it there. So like if you hit a tennis ball, right, directly through the middle, is that going to create rotation?
No.
So, but if you did that and you hit it through there, that's going to create rotation. So that's seen as an eccentric force. Not to be mistaken with eccentric contractions.
Yeah. That's what I was waiting for you to say.
I know, I don't know why they use often it's referred to as torque, the torque force. Or a moment.
Yeah, they're all just the same.
Biomechanics is like that. There's a lot of weird things with it. And also different, multiple terminologies for the same thing. Horizontal flexion. Horizontal flexion is also seen as horizontal adduction.
Right, yeah.
Why can't we just have one? So this could potentially be a 5 mark, and there's your 5 points there.
Wait, so when the moment of inertia decreases, the angular velocity increases.
You guys all got those? Can I rub them off? Okay, right, having to move on. So, next one. This one is actually quite, for me, it's quite a tough one. Quite a tough one. Especially when it comes to the definition and the calculation and the units. Okay? So we're looking at, the last one is now momentum. So we've done angular velocity, we've done moment of inertia, and then we're having a look at angular momentum. momentum is the quantity of angular motion possessed by a body. Okay, so it's the quantity of the momentum, angular motion possessed by a body. So let's break it down. Okay, let's have a look at the calculation. So angular momentum equals moment of inertia, okay, multiplied by angular velocity. Okay, so normally normal momentum for linear motion is, how do we calculate that?
Velocity times mass. Yeah, good.
V. That's a V, not a U.
Yeah, it's like that.
Okay, mass times velocity. Whereas now this is like you're just replacing the mass with the moment of inertia. Because why? It's about the distribution of it. So it's not just the mass, it's about how it's distributed from, because we're talking about rotation. So it's all about the distribution from that axis. Right? So that's the reason why you have moment of inertia as opposed to mass. Okay, does that, are we kind of with that one?
Yeah.
Alright, times angular velocity, so mass times velocity. Okay, therefore, the actual, what they are, so kilogram meter squared times rads per second. Happy with that? So therefore, the unit is, look, get this, kilogram meter squared rad per second. So that's the unit for angular momentum. But the best way to remember it is if you can remember the moment of inertia unit and the angular velocity unit, then you just put them together. Yeah, is that okay?
Yes.
All right. I know it's a bit much, but anyway, so that's that. Now let's talk about, without trying to understand that definition just too much at the moment, because it is a little bit sort of much to take in, we're going to have a look at a video, or a few videos. Oh, I just left that out. Oh, by the way, here we go, look at that. Kitty, this is what we're talking about, how angular motion is created. Don't forget, you've got an eccentric force that acts about the centre of mass, not through the centre of mass, and therefore creates a rotation around that centre of mass, alright? And it's linked to Newton's second law. You can remember what Newton's second law was? What's the equation for it?
Acceleration.
Okay. Force equals mass times acceleration. Acceleration is proportional to force and its direction. Very good. So this here, that's the important bit. The direction is, boys and girls, the direction is that way. We're going to rotate that way. Yeah? And how fast we're going to rotate that way depends on the amount of eccentric force created. But that's just the momentum. So with your legs, right, the eccentric force I created on your legs in that direction meant that your legs were spinning around in that direction, and it was proportional to the force I gave. Okay? So that has now given that body momentum. Now, we're going to have a look after this. How does that, so momentum does not change. So your momentum spinning around didn't change. Your angular velocity changed, but the momentum didn't change. Because once the momentum is in the air especially, is there anything to stop it? Pardon? Gravity won't have an effect on rotation or air resistance, but minimal. Friction in the air, minimal. Ice skater, once they start spinning on the ice and the tiny little contact surface of that blade on the ice, is ice got a lot of friction to it? No? So it's the same kind of thing. So that means that that momentum will just keep going until eventually it starts to slow down. Okay? So the momentum doesn't really change. Okay? For these kinds of movements. Okay? Let's have a look. So, for example, have a look at this. You've got a skater doing a jump and a twist. Momentum, we can tell the momentum hasn't changed because look, it's symmetrical. So, it's a perfectly parabolic shape. If the momentum changed, so that's exactly related to gravity. That's the effect of gravity. Does gravity change? And momentum doesn't change, which means that this arch is parabolic. Otherwise, it would be like it goes up there and then it drops off steeply there. That would be if the momentum changed. But the momentum doesn't change. Okay? It's the same thing as a motocross doing a whatever it is, stunt. You look at the shape of that, perfectly parabolic. Because once that bike has left the ramp with the eccentric force and the torque force of the tyres pushing off, it's got its momentum. That momentum doesn't now change. The only way in which that object can change in the air is by what? Good. Or a moment arm can change the rotational velocity. But the momentum, even if the rotational velocity increases and it spins around quicker, this person, the actual momentum hasn't changed because the shape of their movement, the parabolic shape, doesn't change, won't change. They might spin quicker, but it's exactly the same. Yeah? Now, have a quick look at it, just for a bit of fun.
Up to 60% off sale. Now on and go outdoors. Unbeatable. X Games Los Angeles 2006. Travis Pastrana.
Double backflip, eh? It's the first time it's ever done. Now, this guy has to rely on physics. Otherwise,
as an athlete, you always, every new trick is really special. It's that next level.
I knew there's rumors out there that Travis was thinking about doing this.
This is pre-YouTube days, you know, so it didn't work.
Best that I can, and whatever happens, happens, but I'm not going to leave anything on the table. That's what X Games is about.
And cheering on the 199, go Travis!
Go Travis! Let's go Travis.
so what would he have to have thought about to actually make that land perfectly?
It's moment arm.
What was the moment
arm
on?
and pass towards him.
Yeah.
Did he?
We should have.
He didn't.
Then he might have done three.
Yeah, exactly. He might have got two. He might have over-rotated. It might not have been enough to get three. So if he
The
weight one, he do 2.5.
The weight of this is going to be relevant to what we're doing. The weight of the bike's on the back is the engine. So we're going to try to put it on the back.
What did you see him do with his head?
I didn't see it.
Play
He probably tucks it in, but I wasn't looking.
Yeah, touch the head and he just goes
He looked like he had so much time.
He just folds it down.
Yeah, like it doesn't look that hard. Not as hard as in
I said
Idaho.
this
Travis!
No fan! I know what you mean.
Oh, he tilts his head back. So actually, his arms are fully extended.
Yeah, he's
pulls
his head back.
And his head, he's just keeping his head going back, because if it doesn't, what's going to happen then? If his head doesn't keep going back like that, what's going to happen?
He's only going to rely on his initial force that it'll just stay
That won't be as big of an eccentric force.
It will change.
He's trying to shift his centre of mass.
One, he said a really good point actually. So the eccentric force is created from what?
The moving his body away from the centre of mass.
Good.
Or around the centre of
But
mass.
what's the most obvious thing that's creating that eccentric force?
Him pulling the bike.
Before then,
Just driving up the
the bike.
I said
That's
road.
good.
I said the bike.
Alright guys, come on. The speed at which he's travelling. Okay, so the bike, the rotation of the wheels, and then also, really good point, guys, is that actually he has to, as he's jumped, is it by throwing his head back like that. It's the same as the high board diver, isn't it? So he has to sort of, they have to really throw their arms and their head back, or like a Frosby Fox, similar kind of thing. So that's what he's done there. He's at that's obviously, they've calculated that to the finest. There's another one. What's these rotations? Yeah.
Here's Chisama. 2BU.
This will be sick. This is skateboard. Like how they even stay on the skateboard.
Alright, today is June 27th, 2016. It is 17 years.
is leaving.
Yeah.
He's sort
But,
of
so he's creating an eccentric force going that way. Yeah, good. But then what's he doing with his one arm?
He's
one arm's on the ball, one
So he has to compromise to a certain degree because he needs to have some kind of control over it. So he's got his one arm out. But that, if he tucked his arm in, he might be over-rotating and therefore lose control. So he needs to sort of make sure that he's got control, plus he's got the rotation as well. So there's a lot that really goes into it.
That one's gonna hurt. Let's leave it, it's good.
Let's go, Tony!
No, he's about to do it.
No, he's about to do it, he's about to do it.
He's not.
You might as
He's
well
about to
let
do
it
it.
play. You
He's
might as well
about
let it play.
It's this, sir, it's this. You've got to
Right
watch
now.
it, you've got to watch it, you've got to feel it.
Have you seen it?
Here we go.
It's been building up speed.
That's how they get that. Oh, that is...
That's too cold, mate.
Yeah.
What did you get back to? I think I can have a eat.
We did 948, dude.
Okay, so I'm going to leave it on that, but conservation of angular velocity is something that okay, so I forgot to mention the fact that with angular momentum there's a conservation of that motion. Okay, so the momentum is conserved quantity which remains constant unless an external eccentric force is applied. So what law does that apply to? The first law of motion, inertia. So once that momentum, okay, it's been created, okay, and it's now in the air, it's gone from the second law of motion to the first law of motion while it's in the air, because that, so him spinning like that looked so slow, didn't it, in control. But the speed didn't change. And the actual, the momentum of him didn't change. And it's the same as the biker here, same as the ice skater there. The momentum hasn't changed. But the momentum has to be created in the first place. Okay? Now, when you have a look at the triple axle example in your book, there, it explains, okay, so on page 359, it explains exactly how they use technique and physics to get the triple spin before they land. 3 spins before they land. We did a little test yesterday where you were throwing that leg and the arms around. By having an extended leg and extended arms, and then creating an eccentric force, what am I really increasing? Not yet. What am I increasing? What am I generating? Angular momentum. So the initial thing that I'm looking to generate is big momentum. Then, how do I then increase the angular velocity? Bang!
Reduce moment arm, increase.
Reduce. Good. Joe Hammond, Mr. Biomechanics. All right. He speaks his own language. What does that mean? Oh my goodness. Right. Okay. So generate the momentum. Once the momentum is generated, you tuck everything in, reduce the moment arm, and all of a sudden, just like on the chair, spin, angular velocity increases. But before you land, Sam, what do you have to do? Let's impress Joe here, Sam. Come on. Before you land, you're spinning.
I'm spinning.
What do you have?